Hi everyone, Mrs. V here, and today we are going to be looking at the technique of infrared spectroscopy and how you can use it to get clues about the structure of an organic molecule. This sounds like a good one. Let's get into it. In this tutorial, we are going to take a really simple look at the use of infrared spectroscopy in determining the structure of organic molecules. We will look at how molecules are able to absorb infrared radiation and how to interpret the results of an infrared analysis. Piecing together the structure of an organic molecule uses clues from various forms of spectroscopy. Infrared spectroscopy gives us clues about which functional groups are present in the molecule. Molecules can absorb infrared radiation and gain kinetic energy. There are many ways the vibration of a bond can be affected by absorbing the infrared radiation. The different ways the bonds can stretch and bend are called vibrational modes. Each bond has a particular frequency of vibration, as in how fast each of these vibrations occur within the molecule. For a molecule to be able to absorb the frequency of infrared radiation, that radiation has to match the frequency of one of the vibrational modes of the molecule. This will make the vibrations stronger, but not faster, so the bond will stretch or bend further, but it'll still be doing that at the same pace. Infrared analysis is performed using an instrument called an infrared spectrometer. You can see that these are desktop size these days. When I was at university, the infrared spectrometer took up much more room. The workings are a little bit complicated, but the basic idea is that a beam of infrared light is passed through the sample, and the absorptions are recorded and graphed. The graph produced is called an infrared spectrum. It plots transmittance, which is how much light passes through the sample, versus wave number. Wave number is just how many waves fit into 1 centimetre. When an absorption occurs, there is a trough on the graph, so transmission drops, and we can use the size and shape of the trough to determine what type of bond is absorbing the radiation. The position of the absorption depends on the mass of the atoms involved and the strength of the bonds. Light atoms and strong bonds give us high wave numbers further to the left on the graph. The strength of the absorption, that is how close that trough goes to the bottom of the graph. These are strong absorptions, these are much weaker absorptions. They depend on changes in dipole. So a large dipole produces a very strong absorption. The width of the absorption depends on hydrogen bonding. So strong hydrogen bonding gives a wide peak, like we see here, and less hydrogen bonding gives a much narrower peak. You can look up the wave number of each absorption in a table, and that will allow you to identify which bond is causing each trough. That helps you to identify which functional groups are present in the molecule. We're going to look at some really simple interpretations of infrared spectra now. There's a few characteristic peaks that allow us to identify various functional groups. A big broad trough at about 3,200 to 3,500 centimeters -1 is a hydroxyl group. A strong sharp trough at about 1,075 to 1,350 is a carbon to oxygen stretch. Seeing these absorptions makes you suspect your compound is an alcohol or maybe a carboxylic acid. To tell if you have an alcohol or a carboxylic acid, you need to look for the very strong absorption trough at about 1,700 to 1,750 centimeters to the -1, which is a carbonyl group. You would also see the carbonyl absorption in esters. Here we have the spectrum of methyl methanoate, an ester, but what we don't see is that broad peak from the alcohol. So if you have an ester, then you'll see the carbonyl peak, but not the hydroxyl group peak. Let's try an example. Here are two spectra for a compound that has molecular formula C4H8O2. Can you identify which spectrum is butanoic acid and which is ethyl ethanoate? These are functional group isomers of C4H8O2. Pause the video now and work it out. We'll be back soon with the answer. Let's look at butanoic acid. What features would we expect from the carboxylic acid functional group? Well, we see we have a carbonyl group here. That would give us a strong absorption at about 1,700 centimeters to the -1. Here it is. It's present on both spectra. The hydroxyl group would give a broad trough at about 3,200 to 3,500 centimetres to the -1. Here it is. The hydroxyl group is present on this spectrum, but not on the other one. So this must be the spectrum of butanoic acid. And the spectrum on the left is ethyl ethanoate. Well, I hope you found this video useful and that you're a little bit more confident now in how to use infrared spectra. If so, please give the video a like. And as always, please subscribe to my channel. Watch more videos, learn more wonderful chemistry. I'm going to see you guys in the next video.